Alright, in this video we are going to start studying solvable groups. So first recall that a group G is solvable if there exists a subnormal series, so a sequence of normal subgroups, whose pairwise quotients are abelian. Now of course, this definition's not that useful in general, and so the goal of this video is to give a new intrinsic definition, another characterization, and this one is in terms of what's called the derived series. And so like the upper central series, this is a series that exists for any group, and if it terminates after a finite number of steps, it must be the case that your group is solvable, just like if the upper central series terminated after a finite number of steps, your group must have been nilpotent. So what's the definition? Well, G prime was defined to be the commutator subgroup generated by G with itself. G double prime is defined to be the commutator subgroup with G prime and G prime. And in general, the ith derivative is the commutator subgroup generated by taking the commutator of the two previous groups. Note that you have that G prime is a subgroup of G. It's not too hard to see that G double prime is a subgroup of G prime. To see that, note that the commutators here suppose you take a commutator, well, X and Y were in G, so this commutator is also in G, the commutator of G and G, which is G prime. And so then we see every element, every commutator in this set, the subgroup, well, this set is in G prime. And so that's enough to manage to get that this subgroup generated by all these commutators must be a subgroup of G prime. Same logic will tell you that the second derived subgroup must be a subgroup of the first one. And in general, we'll start to use this type of superscript parentheses 2 for G double prime, G superscript 3 for G triple prime, and so on. And so we actually have the sequence of the derived series. So unlike the upper central series, it starts at the trivial subgroup and gets bigger and bigger. Here we start at G and we get smaller and smaller. So it's always good to try to look at an example. So let's take G to be S4, the symmetric group on 4 letters. Let's just look at what a commutator looks like in a symmetric group. Oh yeah, let me try to always match the definition this textbook uses, product of the inverses times the original products. Well look, it's just conjugating tau inverse by sigma, then multiplying by tau. That's what happens. So what happens if you conjugate if you take a commutator with a 2 cycle. Quite literally, let's just take the cycle 1, 2. Well, 1, 2 is its own inverse, so you're looking at sigma 1, sigma 2, times 1, 2. And in general, sigma conjugate with, or the commutator sigma with any 2 cycle AB is going to be a product of 2 cycles. The first 2 cycles sigma A, sigma B, the second 2 cycles just AB. So we see then that we get these products of 2 cycles, so some of the commutators are even permutations. And in fact, this means that every 3 cycle is going to lie in this commutator subgroup. And since you're talking about the subgroup generated by this commutators, it means you've definitely got the subgroup generated by 3 cycles. The alternating group is going to be contained in Sn prime, just contained in Sn. What one has to argue is that it's definitely not, the inclusion is strict on this side, and then that would be enough to tell you that the derived subgroup is actually An, the first derived subgroup. And, well, how can you show that? Well, let's think carefully here. Why would that make sense? Well, again, what do these commutators look like? It's conjugates of inverse of a permutation. So you're taking 2 permutations of the same cycle type and permuting them together, and multiplying them together. In particular, sigma tau, this commutator, is an even permutation. Because if tau is a product of an odd number of 2 cycles, then this conjugate is also going to be a product of an odd number of 2 cycles. And when you multiply them together, that's going to be even. And vice versa, when tau is a product of an even number of 2 cycles, so is this thing, and their product's going to be even as well. And so that's enough to tell you that Sn prime is a subset of An. So congratulations, we see that G prime is A4. It's a little harder to prove, but you can prove that the second derived subgroup is actually the Klein 4 group, and a particular version of the Klein 4 group, this one, generated by these permutations. And since that group is abelian, it's not too hard to show that the third derived subgroup has to be the trivial group. Why is that? Because when your group is abelian, then the commutator is trivial for all x and y. So we see we get this chain of subgroups. Each whose quotients are abelian groups. A4 mod V is an abelian group, S4 mod A4 is an abelian group. And now we get to our major criterion characterizing solvable groups. A group G is solvable if and only if one of the derived subgroups is the trivial group. for some n greater than 0. And so the smallest n such that this is true is called the derived length of G. Or the solvable length. So let's do the proof. First, suppose G is solvable. Then that means that there exists a chain of subgroups that are pairwise normal. With the feature that pairwise quotients are abelian. Then the claim that we prove by induction is that the ith derived subgroup is actually a subgroup of H sub s minus I. So this actually tells you that any chain of that you could get for a solvable group with this feature has a nice property that it's related to the derived sequence in this way. I should put the for all I quantifier here, of course. If that's true, that would tell you that G to the S is a subgroup of H0, which is the trivial group, which tells you that G to the S is the trivial group, which is what we wanted to show, that one of the derived subgroups is trivial. So we need to prove the claim, and we prove the claim by induction. So you know that the I plus first subgroup, by definition, is the commutator subgroup of G, the ith derived subgroup with itself. By the induction hypothesis, that is a subgroup of this commutator subgroup. Here there is a factor skipping, which is that if H is a subgroup of K, then the corresponding commutator subgroups obey the same relationship. That's not too hard to see because any commutator involving two elements from H, well, those two elements are also in K, so it is a commutator here. And so the smallest subgroup generated by those commutators has to be a subgroup of this one. The next thing we note is that H sub s minus I modulo H sub s minus I minus 1 is abelian. And one of the characterizations of the commutator subgroup, or the derived subgroup, is that it's the largest one such that the quotient is abelian. In particular, that tells you that the derived subgroup of H sub s minus I has to be a subgroup H sub s minus I minus 1. That was a proposition from this previous video. And so that gives us the conclusion we wanted. That's I plus 1. So it boils down to the base case, which is a trivial case because G to the 0 is just defined to be G, and H sub s is also defined to be G. Now the reverse direction, suppose that G to the n is 1. Well, then what do we have? G to the n, which is a subgroup of G to the n minus 1, which is a subgroup of G to the n minus 2, all the way up to G2, G prime, and G. By those propositions again, I guess let's just pick an I. We'll let H be G to the I to illustrate this. The point is H prime has the property that H modulo H prime is abelian. In our terminology, that means G to the I modulo G to the I plus 1 is abelian. So this also tells us, of course, that G to the I plus 1 is normal. And G to the I, these are actually a sequence of normal subgroups whose pairwise quotients are abelian. It's a normal series. Congratulations, G is solvable. So the whole point is that if your group is going to be solvable at all, one of the ways to get a normal series whose pairwise quotients are abelian is to take the derived series. And that's going to be the one that always works. As we'll see in the next video, this actually allows you to prove some pretty powerful theorems about solvable groups.